All right, please.
Okay. Hi, everyone. Good morning. My name is Sadique. I'm from Synsense. And today I'd like to talk about ultra-low power sensory processing for edge devices. That's a mouthful, but you'll see what we are actually up to. So I come from Zurich. That's where my office is located. In addition, we have a few other locations in Shanghai, Shenzhen, and Chengdu. And we are a spin-off from ETH and University of Zurich. And essentially all we're trying to do is enable some business enterprise or neuromorphic devices. And so in that endeavor, we're trying to build hardware, IP, and applications using neuromorphic devices to be able to do ultra-low power computation. And the focus for us is ultra-low power and on the edge. The way we see this going is by having smart sensors, meaning a fusion of sensors plus processors at the edge, and not distribution of them across the cloud. So we do this across several domains, audio, video, health domain, and so on. All of them, the key focus is we want to keep a low latency and low power. And we're trying to do some basic things that we can do on the edge so that you don't have to process all of the data or send all of the data over elsewhere to be processed. In terms of the actual devices that enable us to do that, we have, broadly speaking, 3 categories of devices. The first here is what is labeled as the DynApp CNN. So this is a convolutional spiking neural network chip. And that's all it does. You can feed any type of spiking data to it. It's designed for convolutional networks. So it is designed for vision processing in general. It has up to 9 layers of convolutions, plus pooling, plus spiking on it. The next device, which is SPEC, and we have that here, several of those here. That is a mixture of this computational substrate plus the DBS array on the device itself. So I'm sure most of you are familiar with DBS sensors from simulation and prophecy and several other groups. So we partner with them in order to have this single die solution where you have the sensor plus processor on it, and it's actually pretty tiny. You'll see that is, yes.
What's the resolution on the camera?
So the resolution is pretty low. It's 128 by 128. And that is to keep everything compact. And it turns out for most machine learning applications, you don't necessarily require very high resolution.
So yes. Just pick up a bit, or we can like the component.
There is no microphone. All right. Project. Yes. Yeah. Go for it.
So it's actually on the same die like the sensors, but it's not just packaged together.
No, it's not packaged. It's completely one die.
Nice.
Not loud enough. Just keep reminding me, please.
You sound great here in front of the room. Okay.
Thank you, Gert. Then the last one over to the left is Xylo. So everything I've shown you so far is designed with vision applications in mind. The last one is designed with a low-dimensional signal processing in mind, something like audio processing, biosignal processing, IMU data, where the dimensionality of it isn't very high, but actually most of the information is embedded in the timing, in the time domain. And so that chip is a lot more compact than SPEC. There's only 1,000 neurons on it, but it has better dynamics of the spikes, of the spiking neurons, and you have a more flexible connectivity. So you can enable any types of architectures that you're exploring. Unlike the CNN ones where you're really focused towards convolutional connectivity. Okay. So what I want to do today is kind of give a teaser about the various applications that we've built with these devices and how we do this. So we're going to have a couple of tutorial sessions. We had one yesterday, and we're going to have one today afternoon, I believe. So to be able to use SPEC and Zylo. And so my hope is that I can motivate some ideas of how you can use them, and also come up hopefully together with some additional project ideas of what we can do here with these devices. So first we look at SPEC. What is SPEC? So that's the dimension of it. It's really complex. And so we have it compact so that we can enable embedding these devices into something really compact like drones or mobile applications or robotics. You can always use it for other larger applications, but we want to enable it for smaller devices. So using that, you can do a whole plethora of applications that we built as demonstrators. I'll show some of these, but I have this slide up just to give you a flavor of the different types of things you can do. Primarily, all of these are based on the notion of you get your DBS data from the sensor, and that data is processed using a network that you train in order to accomplish a certain task. Typically, these are convolutional networks that you're using for classification tasks. Here, you have some gesture recognition tasks. Everyone is familiar probably with the IBM gestures dataset. So we use something very similar in order to detect various gestures. Then there are some applications that are more designed towards in-house monitoring. This is like a toy demonstration of our fall detection. And the very last bit is the smart toy applications where you're able to control the toys using some hand gestures. Yes.
All the data that you use to train the models, these are already provided as events, or do you use frames?
So in all of the ones that you're seeing here, the data is from events. The training strategies might mean that you then convert it to frames and train it, because sometimes it's just easier to do that. But in practice, we find it actually a lot more robust if you're able to use event-based training. So actually training in measurements. So all of these were built with spiking neural networks, with the events that we also record on our devices.
What's the time resolution of the spec, or what's the?
So yeah, beautiful question. So this chip is fully asynchronous. There's no time steps. It's really any event produced at the DBS is immediately processed layer to layer to layer. There's no timing. So it's really asynchronous, asynchronous process.
What's the precision of the timestamp?
Because we have the processing alongside the sensor, we don't actually timestamp it during the processing stage. When you want to read out the data to the FPGA, there I believe the FPGA stamps it at microsecond resolution. But in the processing pipeline, nowhere is the timestamp existing.
So one of the good things about DBS is like it has a wide dynamic range. So have you ever tested the motion detection or pulling down detection features on low light conditions or under direct sunlight?
Yeah, so bright conditions is often easier to deal with. Under darker conditions, this is an important ask of the industrial domain there because, like you said, this is the novelty. So we do work on that. But there are challenges that need to be addressed, and we do that to some degree. I think we still have a long way to go in terms of able to addressing low light conditions. The primary reason being the DVS is a lot more noisy when you have low light. And so that impacts the model's performance when you actually deploy your model. So one of the things we do is we try and augment our models using some of the data that we've either recorded at low light conditions or we simulate low light conditions. And that enables us to add some robustness to the application. But it's pretty much application dependent how robust you can get, depending on the complexity of the task.
So for all the models implemented on the chip, when you were doing the training, all the data is like collected using the camera directly on the chip, or if you use some high-res data and like that's it?
No, we use these sensors on the chips.
What's the bandwidth of the processing unit in this stack? Like how many spikes you can process?
Yeah, so because it's all event-driven, the primary metric that is of interest is the number of synaptic events that are being processed. It's not so much number of spikes that are generated by the neurons, because the connectivity, if it's dense, then you will have a lot more synaptic operations. And so the bandwidth we quantize over synaptic operations. So we have 9 cores that are operating in parallel. Each core is capable of processing up to 33 mega events per second. I think the newer generation of chips support even higher, up to 40. And we have, in addition, a couple of cores on the chips that are designed to handle up to 80 mega events per second. 80 mega events per second. I have the unit right there. It's not giga, it's mega.
No, it's
When you say that synaptic operations is a handshake protocol too.
So because it's AER, that involves a handshake protocol. But what I mean by synaptic operations is, let's say a simple convolution requires a kernel. Okay, you have an image, let's say you have a 3x3 kernel, which means that this neuron, anytime it spikes, projects to 9 other neurons.
Right.
So that on our device corresponds to 9 events that are generated internally. And each core then has to handle these 9 events. So that is the limiting factor. So if I had, so let's say I can only handle 9 events within some unit of time. So I can either have 1 event in that unit of time with a kernel size of 3x3, or I could have a kernel size of 1x1 and handle 9 different neurons.
I mean, maybe you have more on the hardware architecture later. If so, then just
Okay, then let's.
Okay.
So yeah, I wanted to. So let's see. So everybody knows DBS now, right? Anybody who doesn't know, that's the question. No. So moving on. So that's the architecture. So you have your DBS array. The DBS array is 128 by 128 resolution. So you have 2 polarities, the on and off polarity. We have some pre-processing of this data that you can have, namely clipping. You can also change the XY axis and flip the XY axis and so on. This is often useful when you're rotating your sensor, when you're deploying it, or things like these. You train it on some data and suddenly you see, oh, this doesn't correspond. So it's often useful to have this right there. Then after that pre-processing, then it goes on to a convolutional core. So there are multiple cores. Like I said, there are 9 cores. Each core has a kernel memory. And that then projects onto the spiking neurons. The spiking neurons that we have on these chips are integrated fire neurons. These are not leaky integrated fire neurons. And this is because for most vision applications, these are good enough. And I'll show you, and you have to trust me, I'll show you a demonstration that these are good enough. So, like, because our focus is what is the minimum computation that we can do to get the task done. So we're really squeezing everything, including the complexity of neurons, to what is good enough. So after that, you can do pooling and then pass on this data to the next course. There is a nuance to this. You don't have to send only to one core. You can also have branched architectures where one layer projects to multiple layers and merge it. We're still, unfortunately, working on the software to enable this at a high level, but in terms of the chip architecture, that exists. What that means is you can do things like residual networks. You can do things like inception architectures, where you have different kernel sizes and so on. And then typically most applications have a dense layer at the very end where you're doing your final reading. On the chip, we don't explicitly have dense layers, but are formulated as convolutions. There is a way to formulate dense layers as convolutions. So a bit more detailed events come from the sensor, go on to the pre-processing block where you're either downsampling, clipping, or XY flipping and so on. Then it goes on to the asynchronous routing fabric. These events are then routed to the designated cores where they need to be processed. Then the data of each of these cores is then put back onto the bus and sent out to the next core. Okay. So does that answer your question?
Almost. So the neurons are implemented really like in dedicated hardware circuits there, or is it some microcode that's running in some processor? Like that's the part I didn't quite.
No, it's dedicated hardware for the neuron, so it's not programmable. So it's programmable in terms of its parameters, like threshold. Actually, for these neurons, that's pretty much the only thing. Plus maybe a couple of others, but it's really minimal. And yeah, that's basically it. There isn't a programmability where you can have more problems.
And in each of these cores, like do you have to think of it, each core is like one neuron accelerator, or is in each core there's then a bunch of these that run in parallel? How do I need to think of it?
No, there is actually one processor that does it.
Okay.
Just one neuron.
Okay. So,
But it's multiplexed. It's all. So this chip is a digital architecture. So we can multiplex it at speeds that. So the limiting factor for us is actually the bandwidth that we can handle, which is much slower than the speed at which we can operate on neurons.
Okay.
Okay. So I just wanted to quickly tease with a few demonstrations. So you'll have that block there. Some guy being very mad at it. And the block over there is going to be shipping. So this is not new. Toby has done this decades ago, I think. The point is we're just enabling that so that, as a commercial product, you can use these types of functionalities. Because Toby had these beautiful demonstrations. And so all we are doing here is enabling that. Then you all have seen the DBS gesture recognition tasks. So we have a modified version of that to be able to do a music player. So this is a simple idea of the types of simple tasks that we could build here really quickly with what we have. We just have to do some data recording, and then maybe for this we'll do some. That's true. So we'll have a live demonstration facility. So Felix is going to show this live, so I'm going to skip this. But essentially, you see it's a simple convolutional architecture. You get the DBS data in front of it, you process it, and it's a classifier that tells you that runs a state machine. Another application is attention detection. So this is in the context of if somebody is looking straight ahead or looking elsewhere. This was a proof of concept that we built for automotive industry for driver attention assistance. So again, a demonstration. So that's not a car. But essentially, if he's looking up front, you have a smiley face. If he's not, you don't have it.
If everything is event-based, how do you deal with this state fullness? Like when all the events go away, like you're completely stationary, there's no events coming in. How do you take care of that?
So that's precisely what we want. We don't want to process anything if there is no events. So the state is held in the neuron's memory potential.
But you could have the subject very slowly rotating.
Yeah, that is unfortunately a problem that we don't really have an explicit SNN solution for it. So for things like that, we rely on a subsequent state machine or something that holds the previous state and then goes on. So it would go a bit in the direction of the music player, but it is indeed a problem when things are super slow. The sensor isn't really responsive to that. So a similar application here. So this is another industrial ask that we had was, can we have a smarter door where it doesn't go off anytime people are just walking by, but only responds when the person is actually going towards the door. So you'll see my colleague walking across it, and the door remains shut. If he faces the door, which is essentially the tripod there, it should open. So it's a little bit of a step ahead of what we have with simple IR sensors at stores. And so that's kind of a simple crux of what we're trying to do, is just adding a little bit of smartness to types of things that we do. Because I don't want to dream of things that we can do with no power. Nothing comes for free. So we're saying it's going to be low power. So we're also trying to do things that are within that budget. Okay, the fall detection, it's again a similar thing. If you fall, it's going to do. So all of this follows the same pipeline. DBS data, your network processes it, you get your classification. Now, everything you've seen so far, you were asking, what about time? Where is all this state? And because I also mentioned there's no leaky dynamics in these neurons. So one big question is, can you then do anything temporal with these neurons, or is it just spatial task? And so this was a challenge we took up on. We had this intuitive notion that we still have a state in our neurons. So it's not that it is not state holding. So we can still use the information in the order of events to process them. Because it's a fully asynchronous processor, we do have temporal information. It's not on clock time. And so this is the demonstration of that actually being functional. This ties in very well with what Guido was showing us yesterday. So this is low-dimensional optical flow. The arrows, Felix, can you help me? Which is ground truth and which is the prediction? Blue is prediction.
Yeah, blue is prediction, green is ground truth.
And so we are actually able to do what is believed to be a temporal task with these devices as well. So the big message I want from this particular slide is, we all think of convolutions as spatial processing, right? When you're working with convolutions on images, you're doing spatial processing. But once you're in spike domain, the same convolutions can do more than that. Because your neurons are not just values, they're state holding. And you can use that if you train them accordingly. You can do more than just spatial processing. This architecture is a simple CNN, but you can do a lot more than what a standard CNN can do. You'll also see a demonstration of this later on. This is the other application that we are working towards, which is object tracking and detecting. This is again kind of going in the direction of some of the older demonstrations from Toby, where you're using some algorithms to track objects. So since we have a CNN core here, we're able to both track and identify the objects of interest. So in this particular case, we've trained this network to track a human.
So I have a question here. So when you are tracking this object, is it like, is the camera also rotating or are you just cropping it?
So you'll see, you're actually seeing the background as well.
Yeah.
So the camera is moving. So this was the primary focus for this particular application is because there are so many distractors that if you have a stationary camera, you don't have. And this task is easier, and I'll show the next one I'll show is that scenario. But this one is a more difficult problem because you have distractors. But the flip side to that is this is the standard approach in standard vision processing. You have an image which comprises of all kinds of things, and you still have to detect objects. Then we wanted to work on. Okay, so everything we've seen so far was low-dimensional image processing. But of course, we have a whole bunch of high-dimensional sensors here, and we want to be able to do that. One of the challenges of working with high-dimensional DVS data is if you're working with spiking neural networks, that also corresponds to a very large number of neurons in your CNNs. And that is not necessarily a great thing because then at some point, you'll have more memory requirements than if you just use the standard CNN. And so we can take some inspiration from neuroscience here and talk about this problem as a split between answering the where question and the what question separately. So what we do here is you take your DVS data, you cluster it, identify object and their locations, and then forward each of these clusters to a CNN to be able to identify what that particular object is. Okay. So a demonstration of this, we have a couple of toy cars. They'll be rolled from a tram. You will not be able to see anything. If anything played here, I hope something did. Okay. So a couple of cars shown under the DVS. It's a high resolution DVS. You'll see what's on the DVS here. These two panels here show you the output of the clusters where the two cars lying in the field of vision are tracked. And then a couple of classifiers are deployed on each of these clusters to identify what class of object is that. Okay. So here, so the slow motion of that here, because I don't know if the video is really working, but this is what's happening. The cars pass through the field of view. They are tracked, and then they are classified. The important thing I want you to take from this is typically all of this happens within less than a second because things are moving. So your processing has to happen fast. You have to be able to identify your objects fast, and you have to be able to process the objects fast. And because all of this is done in the event domain, you're able to leverage this latency and or leverage the low latency aspect of it, and you're able to do this classification really fast. In fact, the latency for this task is somewhere in the order of 6 milliseconds or something like this from the onset of the car into the visual. So now I want to move on to the next device, which is Xylo. Xylo has a slightly different architecture from what we talked about before. This is kind of the external peripheral view of what it contains. It contains a sensory front end, just like Spec has a vision front end. The Xylo has a sensory front end. In the Xylo that we have with us here, we have a Xylo audio, which means we have a cochlear front end there. And there's a onboard microphones on the PCBs that we have. That front end data is transmitted onto the SNN core, and you can essentially program your SNN architecture to be able to do some processing on it. Onto the details of what exactly is that SNN core. So the number of inputs that this SNN core is designed to handle is 16. No more than 16. Now this, because we designed this chip for handling low dimensional signal processing, 16 was an informed choice. If we have a use case where we need a higher dimension than that, then we would build one for that. These 16 inputs can project onto 1,000 neurons on the core. Now, these neurons are leaky integrated fire neurons, which also comprise of a leaky synaptic state. So each neuron has 3 states. There's 2 synaptic states and 1 soma. And you can independently program each of these to have a time constant. These 1,000 neurons can be connected in any which way, including recurrent connections. There is a limitation on the fan in of each of the neurons, so that is an imposition on the sparseness of the network connectivity. Because the moment the network isn't sparse, these architectures are then not necessarily optimal for SNN. So that's the take we went with on this chip. And then all these 10,000 neurons can project onto a small population of 8 neurons, which you can use for readout. In terms of the exact details of what each neuron has, our weights are 8-bit values. Our neurons are 16-bit. All the states are 16-bit. And so the threshold is also 16-bit. And like I mentioned, there's 2 synapses per neuron. Clear so far? Is it too boring? Yes.
Question about this Xylo. From what I understood yesterday, it only propagates strikes, but can you also just propagate the membrane potential?
You cannot propagate the membrane potential, but there is a funkiness to these neurons, which is, so let me take a step back. So Xylo is not fully asynchronous. This is actually a synchronous device. So there is time steps because we would like to have a decay, and this is a fully digital chip. But the liberty we took on the neurons is within one time step, a neuron can fire multiple times. A neuron can in fact fire up to 32 times, and all of this will be propagated. So essentially what it means is if you really don't want to do SNNs and just want to do levels, just bombard currents and make these neurons fire a lot, and that will be propagated. So it's not binary data propagation, then it's a 5-bit data propagation. Yeah.
But is it then actually more efficient to have less spikes? I mean, or if you always send this 32-bit packet, maybe
it is definitely more efficient to have less spikes because of the, I'd like to say the multiplier or the adder that actually works with the weights. But I'm not a chip design guy, so I cannot be sure of it. But it's definitely the case that if you have less spikes, it's better. Any other questions? I'd like to also show maybe demonstrations of this and then an actual demonstration. I'm waiting. All right. So this is a spoken command detection.
Right. Irvin. Right. 1, 2, 3, 4. Go. Stop. Left.
Yeah. I'm sorry. Trust me, worker. Well done, Palmer.
Would you have a live demo here of this tool or?
This particular one I don't have, unfortunately. But yeah, take my word for it, it works. I can show you the video later on my laptop. But again, you're able to do this keyword spotting task with reasonably low latency. For speech, usually the ask is not very high in terms of latency. You're good because you're not going to be speaking at millisecond speeds, you just speak at seconds. So the latency there that we report, to be clear, is not after the whole word is said. It is from the onset of the word occurrence. So depending on the word, it might have longer or shorter time because the feature that is of interest to identify this might happen sooner or later.
Is it using the onboard microphone or?
That particular demo was not using the onboard microphone. The device with the onboard microphone is relatively new. So we have it here, but that demo was not using it.
So do you know how sensitive it is? Is it doing voice cancellation? How sensitive is the processing to the environment?
Yeah, so we have a gain control. Unfortunately, again, not on the one that we have now. This chip is relatively new and we're still working on iteration. But the one that we have, that is our current state of the art, is it does have onboard gain control. There is some noise suppression as well, but nothing much more fancy than that. So in very broadly speaking, it's a cochlear band that is then passed on to a series of sparking neurons. Then there is another block that does some noise suppression on that, so that you filter out a little bit of the background noise.
So is that done with an external microphone? Is it an active cancellation, or is the suppression just filtering or passive?
It's passive. I think it's passive, right? Not an expert. I'll ask you more to define what that is. Right, okay. So there is a couple more use cases in the similar flavor, but in the interest of time, I'm going to skip all that. But just tell you that they work. And okay, so maybe I'll show you this last slide, which is the focus is the amount of power we burn for these applications. We are typically operating in the order of a few microwatts for this. For spec and the vision applications, we are operating typically in the order of a few single-digit milliwatts. For Xylo, we are operating in the order of a few hundred microwatts. Yes.
About this performance, how do you measure the dynamic inference power?
So the idle power is obvious, just sitting there, and then the inference power, you can measure it by the difference of the total amount of power that's being used during the operation versus your time.
But I guess it's very.
It's a mean. It's dependent on your network activity. So this particular numbers are for for this application here, 4 class keywords talking application. Okay.
Thank you.
Somebody will have another question. No. Okay. So all of this is well and fine, but how do you actually use it? So we actually spend a lot of time and effort, just like every one of you, in building the software that enables the use of these devices. And you will have tutorials. We had one tutorial yesterday and we'll have one today. But the general deployment pipeline is as follows. You have a simulation of a network. We have a couple of libraries here that you can use. These are based on PyTorch. Those who are familiar with JAX, there's also JAX support in Rockpool. So you can train your networks in simulation using your GPUs, using your favorite optimizers. Once your network is trained, you can essentially, so this is all kind of done internally. You extract the graph of what's happening in your network, how is the connectivity and so on. And then that is mapped onto the hardware after all the necessary quantization. In practice, what that looks like is as follows. Given you have a pre-trained CNN, so this is an example where you have a pre-trained CNN. You don't even have a spiking network. You can convert that using some automated methods to a spiking network. Then you can convert that spiking network into an architecture that is compatible with our chips. After that, you just say network.to my device. So this is a simplified form of it. There's at each stage you can do optimizations, but this is the crux of what you need to do in order to deploy your models. So we're trying to keep it as tight as possible to API that you're familiar with. And all the dirty stuff goes inside the libraries. A similar API exists for Xylo because the connectivities that Xylo supports is an order of magnitude more. The corresponding programmability also exists in Rockpool for that. We will not go through the details of this. All these dev kits, both the dev kits are available. You can purchase them, or we have them here. Let's build something cool with them. And thank you very much. Now, please don't clap. Maybe if the demo works, then we can clap. So now, so we have a couple of demos, the division demos with spec, just to give you a flavor for what it feels like to work with them.
I have one general question. So you worked with analog circuits, you had a version that is using asynchronous network instead, and now the Xylo is synchronous digital. Is there maybe some insights you can share what the reasoning is? Like, did you learn something that others should also know?
So, because we are a commercial enterprise, we care about scaling. So it is possible to build one application on one chip with all the mismatch and everything. But we need to be able to then deploy the same application on 1 million devices and know that they will work with the same certainty that we expect. And so this is the easiest path to getting there as a start. Our devices still have an analog component to them. The front ends are analog. So there is still a certain amount of variability in them. And I think somewhere deep inside, we all still hope and believe that analog will rule. But this is the quickest path to getting to our first success point. Yes.
So the power consumption reported always like the CK the chip, right?
Correct.
But what the power consumption of the whole board?
That would be higher. I cannot tell you. I'm not sure there is actually a measurement for the full board. So the full board has full-fledged FPGA and the USB interface to be able to monitor all of this now. The intention is that when you deploy things, the FPGA and the USB doesn't exist. We also have a development board. Maybe we'll hear some music. We also have a development board which does not have all these extra peripherals. And that is to actually validate, can you realistically deploy these things in the real world without additional post-processing on a PC or something like this. And those are, you would get a better sense of how much the total power you would be burning is, but I don't have that number.
Yeah, what are the main improvement direction you are targeting to reach the market? More, you want to stay ultra low power like that, like you have some applications in mind, or do you want maybe to scale up and accept a bit more power, but really push the accuracy to, I don't know, state of the art or something like that?
So we have both types of clients, and the third type I'll tell you. So one wants low power, the other wants very high accuracy, the third wants everything for free. So we kind of have to balance those three. At the moment, the primary focus is to keep things low power, but we're also working on an additional line of, so the Dynap CNN that I showed you in the very beginning, we're working on enabling the ability to work with larger networks. So there, in fact, power is then not going to be in the same order as with what we have now, but it will enable us to do other applications that we are currently doing.
Yeah, let's try how this will work with the Zoom transmission. There might be an incredible lag. So this is a demo of a music player, and I can control it by gestures. So I can wait and then give a command to skip to the next title. It should be playing audio, I think yes. Okay. Let me try to just use the laptop. Here's something. Let's pause that. Let's just it's paused on my screen. I don't know, maybe it would make more sense to connect via HDMI.
Yeah, we could look for the live demo. Let's directly connect you. Unfortunately, it's all the way over here.
Oh, okay.
That would be the problem. I think we can
5-second latency.
Yeah, I mean, we're about 5 seconds behind, so you can kind of imagine it. The other option might be, you have an Ethernet cable on that computer. If you will get a faster connection to that.
Maybe much better.
Oh, there we go. And that works.
Biggest that I don't see.
Oh.
Okay, so I think I lost it now. Right here. And it's longer. It's so now the first gesture I skipped to the next song. Okay, let's. Okay, let's move to play.
Neuromorphic network.
Turn the thing 180 degrees and
Yeah.
stand outside. You can see the fast.
Yeah.
All of you are going to start waving.
The Zioma, all right.
Maybe it's easier to just do it after
Yeah.
Yeah, maybe we can have an informal demo just
Yeah,
on the
maybe
coffee
you just
break.
come over here.
Yeah.
Sure. So there is this one and the optical flow one as well. You can see them both. What we wanted to show was that it's all real time and all of that is happening on the chip. The only overhead is all the events that are being routed to the PC to be able to visualize it. And unfortunately, this laptop isn't the greatest graphics tool. So some of our demonstrations have become slow and laggy because we're not really building these for laptops. But essentially, that's the limiting factor is the USB and then the visualization, which ideally we shouldn't have on that.
I thought the limiting factor is the network and Zoom.
Yes.
Well, in this case, yes. But if we were to just use the screen, there is one optic flow demo that works pretty fast on the device, but then the plotting of the optic flow, the arrows that it predicts, is kind of slow then. But we can show it.
So the point is we have a couple of things that work. Let's do something with them. If you have ideas, please come up to us. What I would really love is if we can use both of them into one application for some kind of sensor fusion. But open to ideas. Cool. Maybe an invitation for anybody who hasn't done deep learning, or at least deep learning with spiky neural networks. The API is pretty simple. So if you've done any amount of Python coding, we can get you to the next step.
I have a technical question for your projects. How easy or fast can you reprogram weights on the different setups?
It takes a few, maybe a second-ish.
Okay.
Because typically you have to load all of the memory through the USB.
Yeah.
So it takes about a second-ish.
And you cannot reprogram just specific weights. You have to.
You can. But there is no explicit guarantee that I can give you that it's only going to take X amount of time.
Okay.
So we just put like a second of sleep anytime we write, just to be sure.
Okay.
Break time, right?
Yep. Yes, we had a break and then, so we're in the coffee break right now. And then at 10:30 is the audio talk on overt, mouthed, and imagined speech activity from intracranial recordings.
So in the meantime, anybody wants to see these demos actually in realistic time?
Great.
All right, thanks, Vikash. Yeah, so as Vikash mentioned, I'll talk to you today mainly about some of the work that we've done recently related to intracranial speech decoding. I'm going to focus on one particular aspect, and I believe Christian Herf will talk to you next week. So I collaborate with Christian. I'm going to kind of tease a few of the results I worked on with him, but focus on one of the more recent papers out of my lab. So I'm not sure of everyone's background, but I'll give you a quick overview on the types of signals we're working with. So we are working with patients that have intractable epilepsy, that are looking to have resective surgery to treat their epilepsy. So we are not studying epilepsy. We are just using this unique access to patients to run neuroscientific and brain-computer interface studies. So traditionally, most of these patients were getting implanted with electrocorticography grids, which you see on the left-hand side there. So some of our results were based on speech decoding from electrocorticography, or also known as ECOG, which we were getting very nice results because this gives us nice localized coverage of speech areas of the cortex itself. But the clinical field has shifted to what's known as stereotactic EEG, which you see on the right side there. So using depth electrodes, so we don't get generally as much coverage of the cortical surface, but we're still experimenting on what can be done related to speech decoding with this different type of electrode. So again, those of you that aren't familiar with measuring signals from inside the brain, specifically kind of more macro scale signals, not single units, one of the things that this affords us is the ability to see broadband gamma activity. So this is a seminal paper by Kai Miller that shows, particularly for the motor areas, the difference between the low frequency and high frequency activity. So the low frequency activity are generally thought of as oscillations. And you see here that actually the power is higher during rest and decreases during movement, whereas the high frequency activity, and in this case, broadband gamma activity, which is generally believed to be above 70 hertz, has the opposite effect. But the other thing is that this effect is actually much more robust than tracking the low frequency oscillations in general. And that's how a lot of progress has been made looking at these signals inside the brain. So just again, to illustrate this, so that was in the frequency domain, but Kai also had another nice paper to illustrate how localized this is for detecting finger movements. So if we just look at the power envelope of broadband gamma, we can see how nicely over time that envelope tracks in individual finger movements. So each, in this particular illustration here, each area of the hand area of the motor cortex is illustrated by a different color. So when the broadband gamma activity changes in that particular electrode, you can see it nicely and precisely tracks the temporal trajectory of the individual finger. So just giving you a sort of a sense of how much information and power lies in utilizing these broadband gamma features. So what we and others do is attempt to use these features for looking at speech activity in the brain. So ultimately, what we're trying to do is develop a speech BCI or a speech neuroprosthesis. So the kind of logical way to start to develop such a model is what you see on the left, right? So we're simultaneously recording brain signals and acoustic speech with a microphone. So we have access to these synchronized signals. So can we develop a decoding model that estimates the acoustic speech from the brain activity? Okay, so that's the basic concept, but to help a disabled individual, what we want to do, so when I say disabled, someone that is unable to speak or maybe has some severe speech disability, can we have them attempt to speak or even imagine speaking and use a similar brain signal decoding model to synthesize the speech ideally in real time? So what I'll talk about some in this talk is the difficulties going from the model on the left to the model on the right. So developing these models on the left using actual speech generally do not translate well to decoding imagined or attempted speech. So just I'll give you a little history of kind of where we came from leading up to the main results that I'll present. So back, I guess this is 2016, I worked with Gervin Schalk's group. He's at, or was at the National Center for Adaptive Neurotechnologies. He's now with the Chen Institute in China, and also John Brumberg on a study. So this was particularly ECOG, and what you see on the left is the superposition of ECOG electrodes from 8 participants. And what we did was we had them read text passages and looked at how the acoustic speech waveforms were correlated with gamma activity as they were speaking. So on the right video there, you see a little timer in the lower left-hand corner that's going from a half second before speech onset to a half second after speech onset, where speech onset occurs at 0. And you can see the spatiotemporal progression of the activity as they're speaking. So this is average across 8 subjects, but kind of as expected, a few hundred milliseconds prior to speech, we see activity in what's known as Broca's area. So, and by the way, the front of the brain is on the left-hand side, the rear of the brain's on the right-hand side, and we're looking at the left hemisphere, which in general for most people is the hemisphere associated with speech processing. So we can see prior to speech, the speech planning areas, Broca's area, and even premotor cortex, which is the motor preparation area, and this is specifically related to the mouth motor cortex becomes activated. And then after 0 milliseconds, so around 0 milliseconds, we also see the motor cortex active. And then after 0 milliseconds, it's largely the perceptual feedback, because you see the kind of the big blob sort of in this central that occurs around 0 milliseconds is really them hearing themselves speak. So these general regions were known prior to this, but this is one of the first studies to show kind of how this can be mapped out with resolution on the order of tens of milliseconds on the surface of the brain. So again, just another illustration of what's possible using the broadband gamma activity. So one of our next studies was actually looking at how we can use this broadband activity to decode speech. And this is again with participants that had ECOG grids. Now, just a point of clarification, this is the only data that I'm going to present here. These patients actually were tumor patients, so they were going in for surgical resection of tumors. So these grids were implanted during awake craniotomies, and what this allowed the team that collected this data to do was more precisely position the grids, and these are actually smaller scale grids than are typically used clinically. So they were able to position the grids more precisely over the speech motor areas, which gives really nice data. And you can see over 6 subjects that we had pretty consistent coverage. So I'll just quickly present the decoding results. Christian, I believe, will go into much more detail on this, but just to give you a sense of what it sounds like, hopefully oops, I probably need to, I think when I hit share, let me quickly reshare, because I think when I share a screen, I need to activate sound. 1 second. Screen share. Share sound, okay. Okay, so hopefully you'll be able to hear the sound now. Okay, so what you will hear is the word the patient said, and then followed by the word that oh, sorry. What point did I drop off?
We lost you. We lost you right at the screen share.
Okay. Okay, sorry about that. Let me redo that. Okay, you're able to see the slides again?
Yep, it's back up.
Good. All right, sorry about that. So, so what you'll hear is the patient's spoken word followed by our reconstruction of that purely from the brain activity. So I realize there's a bit of priming there, but it'll give you a sense of the overall quality. So we actually published 2 papers using completely different techniques to do this reconstruction and synthesis. So I'm not going to go into those because Christian will likely talk about those next week, but just to give you a sense of the decoding quality and the synthesis quality that we're getting, I will play this now.
Page, page, pave, pave, Persian, Persian, rush, rush, shook, shook, steer, steer, vision, vision.
Okay, so you can see that, and obviously this is one of the better case scenarios we had, but it does in some cases intelligible, or at least approaches intelligibility. And this is, quite similar to what some other groups have achieved recently. So now the question is that at least the clinics we're working with, there are still a handful of clinics that are using ECOG, but at least the clinics we're working with primarily use SEEG now. Can we do the same thing with SEEG? The other big question is, so that was, those models were trained using overt speech. All right, can we do it with imagined speech? And can we also do this in real time? So, if it were up to me, I think I would take maybe 1 or 2 of these at a time and study them. But my collaborator, Christian Herf, said, let's try to answer all these questions at once, or at least, do a case study that attempts to look at all of these at once. So another study published in 2021, again, is looking at both imagined speech, SEEG, and real-time synthesis. So again, I'm not going to steal Christian's thunder, but I'll just quickly play some the results obtained using the imagined speech. So these were SEEG. This is actually a single SEEG patient. The other thing I want to point out is that this was done in the Netherlands. So the patient is speaking Dutch, and I want to fully acknowledge that even if you do speak Dutch, these words wouldn't be intelligible, but I want to give you a sense of the quality of the reconstructions that we can achieve here using SEEG. Okay, so again, so that probably didn't sound like anything intelligible. So there's a couple reasons for that. Well, one obvious reason is that we're not getting very good coverage of the speech areas like we do with ECOG. Number 2, we're actually using a much simpler decoding model so that it can be done in real time. And I believe, I don't think I have the slide here, but I think we're on the order of 10 milliseconds latency with this decoding. So this patient is hearing the feedback of the decoding model. Those are at least 2 of the reasons why it's not working as you might expect in terms of intelligibility. But what does work very nicely, as you can see, is kind of the onset and offset detection of the individual words, even for the imagined condition. So again, this was the imagined condition. So we believe that if we were able to do this with ECOG, or maybe even the combination of ECOG and SEEG, we could achieve much better results. But again, I'll let Christian talk about this and probably some subsequent studies that he has done. So what my PhD student focused on over the past year or so is basically to look at why generally don't we get as good decoding when we train a model on actual speech and apply it to imagined speech. Okay, so this was recently published in Neuroimage earlier this year. So I will talk about exactly how this study was designed and some of the results. So we used 7 patients that had stereotactic EEG, and these are again epilepsy patients. So what we really wanted to look at is, we had a condition where they imagined speech. We had a condition where they spoke aloud. And then we also wanted an intermediate condition. So we're kind of looking at this as degree of behavioral output. So actually speaking is high behavioral output. Imagine speaking is no behavioral output. And then we wanted an intermediate condition, which we called mouth speaking. So they would move the articulators without vocalizing. So we had the patients read a sentence that appeared on the screen. They also simultaneously heard the sentence. There was a pause, so they basically retained the sentence in memory. There was a cue for them to speak it aloud. There was a pause. There was a cue for them to mouth it. There was a pause, and then there was a cue for them to imagine the same sentence. Okay, so what we did with this data was to ultimately we wanted to figure out which neural features were most contributing to the models for predicting when the person was actually speaking versus imagining speaking versus a mouth speech. So we actually were not modeling kind of the full acoustic waveform, and that was largely to simplify the problem because there are a variety of issues with quantifying and qualifying the accuracy of reconstructed speech. So we wanted to simplify it a bit. So we switched to speech activity detection, or sometimes known as voice activity detection model. So we were simply trying to detect the periods when they were vocalizing versus not vocalizing, or not just vocalizing, but were imagining versus not imagining, and so forth. So we not only used the gamma features, we also looked at other frequency bands, and there have been a few recent studies that have evidence that, so just a little bit of backstory. Once people recognize the power of broadband gamma for decoding, a lot of studies neglect the lower frequency features, but there have been a few recent studies that show, okay, the lower frequency features in conjunction with broadband gamma can improve the decoding model. So that's why my student included these into the decoding models. And these are all causal models. So basically taking the theta band, alpha band, beta band, and broadband gamma, and building decoding models to predict speaking versus not speaking, or imagining versus not imagining, and so forth. So one of the biggest revelations that came out of this comparison was that, so what we did was looked at which features. Now in this case, when I'm calling features, this is largely focused on looking at the electrodes that contained features that were relevant to the respective decoding models. And something that came out of it that wasn't actually expected. Now we had some sense we may get something like this, but it sort of worked out even better than we expected, is that what we're calling it, we saw a nested hierarchy of the organization of electrodes according to behavioral output. So what I mean by that is that any electrode that was relevant for the imagined decoding models was also relevant for the mouth and overt decoding models. So if you look in this upper right-hand Venn diagram, that kind of gives you an idea. So then there's a subset of electrodes, which is in orange here, that were only relevant, that were relevant for overt and mouth, but not imagined. There's a subset of electrodes in those models that do not work on the imagined, or are not selected, I should say, for the imagined speech models. And then there's another smaller subset of electrodes that only are selected for the overt speech models. But the interesting thing is we found no exceptions to this rule in our particular data. We've talked to a few other investigators that claim that they have some data that does kind of break what we found here, but we have not looked at that data, and we're not claiming that this is not possible with the particular electrodes that we have access to and what we sampled followed this model perfectly. So basically what this means is that when training an overt model, so a model on actual speech, it's likely selecting electrodes that aren't predictive of imagined speech activity. All right, so this is again what we call the nested hierarchy. The figure, so the figure on the left there shows the color-coded electrodes, and if you can see, there's little gray electrodes. These are all the other electrodes that were not selected as relevant for any of the decoding models. So basically, the green electrodes are relevant for all models, overt, mouth, and imagined. The orange electrodes are only relevant for mouth and overt, and then the blue electrodes are only relevant for overt. So as we would expect, most of the blue electrodes are in the auditory regions, likely a result of the acoustic feedback. So just the way that the analysis was designed with the speech activity detection, it is possible to design a reasonable model incorporating a causal prediction, incorporating acoustic feedback, just the way that the analysis was designed. And we fully recognize that, but the reason we left that in is because that acoustic feedback is not available for the mouth and the imagined. So this is more for comparison purposes. Okay, but it is sort of telling as to why these models may not be transferable between, again, something like overt to imagine. So I'm going to skip over the figure in the lower right hand corner, because I think I have another figure that better represents what's going on here. So this basically looks at the models trained on one speaking mode. So when I say speaking mode, overt, mouth, or imagine, and tested on another speaking mode. So what we've presented in the past, and which many other groups present, is kind of showing what happens when you train a model on overt and test it on overt, sort of like the some of the previous results I presented. So you get pretty nice decoding accuracy. Now I realize that this is speech activity detection accuracy versus something like a speech synthesis, but I think the analogy holds here. So what we see is that if you take that same overt model and apply it to mouth, which is the kind of the lower behavioral output, and then apply it to imagine, which is the lowest behavioral output, you see this steady decline in performance. And this kind of nicely ties back into what we found with the electrodes that were being selected for these different models. But the other thing I want to highlight here is that, so what we found is that the electrodes that were relevant for the imagine decoding are also relevant for the overt and mouth modes. So when you look at the right bars on this figure here, the performance is pretty stable. Now it's obviously lower than what's achieved by applying overt to overt, but that scenario really isn't representative of what we would ultimately need to apply for a disabled user. So what we see on the right there is that these electrodes, right, if it's trained on imagined, what we already determined was that those features selected for imagined models are also relevant to mouth and overt models, and we can see it here in the performance. So the performance is relatively stable when you train features on imagined data. Okay, a couple other things. I'm going pretty quick, but a couple other things I want to point out here is that another unique finding here is that previously a lot of studies were focused on the speech cortex, speech motor cortex. Now we're getting sampling of deeper structures. So we took a look at kind of the relative depth of the electrodes, and we did this in a somewhat crude way. We created concentric spherical shells and counted the number of electrodes inside those spherical shells. So you can see the relative depth level, where one indicates superficial electrodes, which are largely on or near the cortex, and then the deeper electrodes are in deeper structures, likely near the hippocampus, for instance. But what we see here is that the yellow dots count how many electrodes, and specifically these are the electrodes that are relevant for these models, are in each shell, and then the average speech activity detection performance of those electrodes. So you can see relatively few are in the superficial regions, but those ones in general contribute the highest decoding accuracies. Okay, and that's kind of expected, and it's also illustrating that we're not getting much sampling of the cortex. But the other interesting finding is that the electrodes at these intermediate depth levels, which by the way are largely white matter, there's quite a few of them being selected, and they're getting above trans performance. So we recently presented these results at a few meetings, and most recently the International BCI meeting a couple weeks ago. And a lot of people have questions about how are you getting useful activity from white matter, and that's, I think, still remains an open question. But at least from the perspective of building models and decoding, it's working. So what that's actually representing, because this is, these are myelinated fibers largely, what that's actually representing is a different question, but it does seem to be contributing something to the decoding models, even if it's something like a suppressor variable or having something to do with noise cancellation or so forth. So that's, I think, another interesting finding. And then, I went through this pretty quickly, but maybe we can save some time for more discussion or questions. My student also followed this up with some other analyses that weren't in this particular paper. So these are kind of smaller analyses on, I think, a smaller subset of patients, but he also looked at building models purely from the gray matter electrodes, purely from the white matter electrodes, and purely from combined electrodes, and showed actually the white matter electrodes were nearly equal in performance to the gray matter electrodes, and when they were combined, performance improved. So the other thing he did, which is quite interesting, is rather than just comparing these models that were built on speech activity detection, he wanted to see if he could build models that discriminate whether the person was speaking overtly or whether the person was imagining. So if that's the case, right, there should be different neural activity if he can reliably discriminate whether they're speaking versus imagining or speaking versus mouthing. And that's basically what he found here on the right figure. So he compared building the models just on the non-speech intervals, which you would expect not to have much effect because there's really not much behavior or even imagined behavior there. So that's what he found. There's just chance accuracy, but he was successfully able to build models that discriminate, the overt mode versus imagined mode and so forth. So, and another piece of evidence supporting that there is in fact different brain activity going on between these different speaking modes. Now, what we haven't yet answered is, so what can be done to, improve the model? So right now, these results sort of characterize and show that this is likely why the overtly trained models are not generalizing to imagined data. And we have, maybe some insights as to what's going on, but we haven't really dug into that deeper just yet. So in that sense, it might not be fully satisfying, but we're continuing to make progress on that. So that's my last slide. I just want to acknowledge all the people that contribute to the data collection and data analysis for some of these projects and some of our ongoing projects.
To generate from Lego features, that's a ultimate task. But before we kind of simplify it a little bit, we're going to generate the image, but we're going to generate it from just kind of random starting position. So we're going to ask this model give us the image, any image. So it's kind of simplification, the first simplification. Going to start from now. Right? So for this type of generative models, you probably recognize, right? Going to label the image, what other model you know. Yeah, it's obvious, right? And what else? Yes, variation of autoencoders, that's quite good. So this is the kind of very famous architecture right now. There are flow as well, less and people back in like 5 years ago, maybe 8 years ago, they would do the back propagation. There is a way to do it for backprop, really slow, but you can get images Google. So, and you probably know the GAN have some trouble when you try to train them. Way has some other issues. So today I would say that diffusion models are best in terms of the quality, and they are very stable to train. So it's kind of good thing about them. Have very simple loss function. So what does the diffusion model have? What does it learn? So imagine that we have we'll try to give it intuition here. Imagine we have a bunch of samples, images, right? And one thing we have, and probably we even have some labels for them. You get the cat, and you get the dog here. So what we want to learn is we want to learn kind of manifold. Like imagine these images are projected into some simple 2D space, right? We have a bunch of samples, they are projected. We want to learn this manifold. We don't want to just learn the images, we want to learn the probability distribution of the possible images, and we want to be able to kind of sample not just one image, but we want probably to have something in between images as well. So what people say is we're trying to learn this manifold across multiple images. Across the images, we're going to feed into the system. So what diffusion model does, it learns not just this manifold, it learns, you can imagine the vector field around those some image samples. That vector field is kind of pushing from any position that you are going to ask in the space. They're going to be a vector field, multidimensional vector field, that is pushing towards this manifold. So that is what makes it very nice and very stable. So it doesn't, the model does not really learn the manifold itself. It learns this vector field that is pushing towards the manifold. So we can start from any position, and we are going to be pushed into the manifold of our data. So, for instance, if you look at the variational autoencoders, what they do, they don't really, they kind of learn just a little bit around you take an image, and then you can inject some noise into the variational autoencoder, and it learns some information around that image, but it's kind of small cloud around the data. And if you have a sparse cloud, then you hit some point here, and you will get like shit. Or if you get here, from here, it's really hard to arrive to that position. And usually the result as well, because you inject noise, you get quite blurry results. So that's variational of the encoders. People spend quite some time optimizing, but that's fine. So GAN is a bit better. It actually learns this, tries to learn this manifold, but it doesn't learn this kind of pushing thing here. So it becomes hard for it, like if it works, it works, but otherwise sometimes it just collapses because this manifold can be quite hard to learn and so on. So the diffusion model, it's like a very simple, almost ingenious idea that we are going to learn a vector field around that is pushing us towards this manifold. It makes it quite stable. So, okay, so how do we learn this? Where do we get this vector field? So idea is very simple. We're going to get this vector field by taking our data samples here and by destroying them step by step. And the more we destroy, we destroy it and it goes in opposite direction, right? It goes away by destroying this image, we're going away from the manifest. So it's kind of opposite process.
So it's diffusing.
Sorry?
Is it diffusing?
Yeah. So we get, this is the diffusion, right? We add more noise and we're going away and by that, we're exploring the space around our manifold. And we're learning from that. So that's kind of the simplest form, simplest idea behind all this diffusion models. So, okay, and we can basically, now we can take a look at this particular kind of path here, right? What is happening in that path, on a single path when we are training the model. Obviously, you understand that once we have this vector field, it's quite easy to sample the data. We start from any position, we're using this vector field and we arrive here. And for training, we destroying the images, destroying it, and creating this field around. So how would we destroy the image?
Add noise.
Add noise, exactly. Add Gaussian noise. We're going to add Gaussian noise. So and if we look at this path, right, we can now draw a bunch of images here. Usually, in an original paper, they would suggest to do it 1,000 steps. So here it will be, they call it T 2000, and this is a T equals 0. T equals 0 is the original image, the good one, right? And then step by step, we're going to add more noise, and obviously it's completely noise. So, like if we write it like one step here, the one step here is very simple. It's, let's call it X, that's our image, right? The vector X. And we add some Gaussian noise to it. And of course, we add a little bit of it. So we're going to say it's like let's come up with some parameter alpha. Okay, this is the gist of it. This is the one step of the destruction. We take our X, the image, right? We kind of reduce it a little bit and we blend in a little bit of the noise, right? And the noise is, in this case, the noise is the Gaussian, which is around 0 and with the distribution of 1, mean of 1. For images, that kind of makes sense, right? So this one step. Now, and we start from xt and basically xt plus 1. This is xt and sorry, x small t and small t. Well, xt, yeah, and xt. And that's how we get this chain. And we're going to train using that chain. Now, in the paper and in the real implementation, you will see that because the Gaussian noise is really nice, and we can really easily combine a lot of Gaussian, so we can combine these steps. We can, instead of doing it step by step, we're going to prepare all this in one go. We're going to generate xt image by starting from just getting our initial image and adding some noise to it. So we can generate all those positions by just adding various amounts of noise to the original image. So we don't need to do it step by step like that at all. And in the paper, you will see with some magic, this constant will become a little bit different. It will become the square of A alpha and square of 100 because of the noise, because how the noise behaves. So that's it. We need to calculate these alpha parameters, and we need to just to have a Gaussian noise, and we add it to our original image. That's how we get all the training set. And we're going to back off to learn that. So what would be the best neural architecture to learn this vector field using this image? Exactly. Was the question?
Yeah, it's actually a question because I'm not understanding what you are learning here. Is it the alpha or?
No, here it's just how do we prepare the training data, not learning data.
Okay.
So the training data is that just how we destroy the image.
Okay.
With each image, yes, 1,000 samples, right?
Yes, from each image, we're going to make 1,000 samples by adding a variant different amounts of noise. And this alpha here is basically for each of this, you calculate a little bit different alpha. This is how you know how much noise you have to inject. This is quite important. You cannot randomly inject noise. It's important that it follows certain this alpha values, they need to follow certain kind of pattern.
For the training data you're now creating, are you taking the very destroyed image as, so from the very destroyed image, I want my perfectly clean, or I want my next level of less destroyed?
No, from the completely clean image, you generate all of them, but not, you don't need to do it sequentially. That's paper. You can just in parallel.
Yeah, but when I'm training my backdrop network, I'm giving it input data and output data.
Yeah, that's true.
And the input data.
You will write in a second. Yeah, sorry. There's one trick there.
So since it's a Gaussian distribution, is equal to 0 the top point of the Gaussian distribution, and you're like sort of adding noise in both directions, but then equals to +1 and equals to -1, is that the same noise or is that different noise?
Different amounts of them. Yeah, the noise pattern will be different. It's like you just generate. For every image you can generate, you sample it and you sample the new distribution from Gaussian for every image. Then just multiply it a little bit. This is just a scalar constant.
I think what he's asking is, are we using the same noise mask for all 1,000 times that?
Noise mask? What
the same noise pattern?
No, ideally it's a difference. You just sample from Gaussian every time. I don't know what would you probably could use. I think it would be better. I think it will learn something else. You need to sample it every time for every image.
So you're always making it more entropic. Has anyone gone the other way? Because it sounds like you give an image which is just black. This results, the 1,000 example is maximal.
Just complete noise, yeah.
But most of your real samples are going to have some level of entropy. You only ever go up.
Yeah. So although our images have some entropy for the
very close to
right now, they assume they are close to 0. So there are other. This is all of it. Not all of it, but there are some applications like the ray tracing when we want to. It kind of resembles it. I think it came from that direction as well. And there it's a bit different because you have like in the ray tracing, you have the noise implicitly in the images. And don't do that. This approach is only when you have it in the image that you assume there is no noise. But it's not right assumption, but good enough.
So very good question. So here, as we are adding noise step by step, right, there's a connection between T and T+1. But when you're adding in parallel from random distribution, do you still have that connection of like with the T-1 or no?
No,
right?
It doesn't really matter. It's just I'm just following what's in the paper, so it's like you can generate it step by step, but it's just this is something they use in the paper and we use in implementation. So
how to parallelize it this way.
Yeah, and it's just for the parallelization. But I wanted to clear it because just how they do in the paper, so it's follow the implementation. Okay, and we agreed we're going to use the autoencoder for that, right? So we're going to use the autoencoder. Autoencoder is pretty much like there were people using the variation of autoencoder. It's pretty much off the shelf existing autoencoder. It's usually people use the same one, UNEP. It's very well developed, so that's it's a good building block. So in the paper, in the diffusion model, in the paper there is just basically they just use vanilla, right? And for people, I don't know, everyone knows what UNEP is.
Should I input now to mention the same?
Yeah, the same. You have the same like image here comes in. Say resolution is 128 by 128. Out goes out the same thing, 128. So here we have just a bunch of convolutions, and here on the opposite side, it's a like drawing. This is like every layer is a convolutional layer, and here we have it can be a transport convolution, or it can be it can be stride convolution. But doesn't matter. It's just a bunch of convolutions. And then with every convolution step, we're going to reduce the resolution of the image, and we're going to add more channels to it. So basically, and here we're going to have like a very narrow bottleneck where the resolution is very low, but we have a lot of channels, a lot of depth, a lot of features. And the important part of the unit, there's key connections here everywhere. Yeah. So it's easy to train. People did that. Of course, there are some bunch of normalizations here, and all of it is kind of pretty much standard by now. You just take the unit, plug it in, it works. Yeah, so it works as well. Like that is why it's easy to train, because people made so much effort into units, how to train them. That's it. Basically, the training here, we prepared all those training sets, right? So we're taking basically here what we are putting as an input. We're going to tell it X. T, and here we're going to get X T plus 1. That's what we're going to train, almost. But in reality, people, instead of training from image to the more noisy image.
Is it T plus 1 or is it from T plus 1,000 back to? Yeah.
From T, it's in the direction. But what we are learning here, it's actually, instead of passing T plus 1, what we're going to learn here is a noise, amount of noise. So it's actually kind of T plus 1 minus XT. This is what we're learning. We're learning the noise. Not the transformation from the noisy image to from image to a more noisy. We're going to learn the noise. So it is a bit of a, I mean, people say that it is better. Logic here is that it is easier to learn a noise rather than learn the features of the image in general, right? However, if you look at the map, it's kind of the same in them. So it's a bit of a maybe, I don't know. I mean, you can try. People who try to say you get the same result, but conceptually it sounds that it is better to learn noise. So you can try to prove yes or no. But in a classical implementation, you learn the noise, not the image, but you learn the noise that you added yourself. So it's good because you have the control over all these parameters. So there's no unsupervised in this sense. It's all absolutely supervised. So it's much easier to train than GAN. So, and which loss function they're going to use? So in the paper, they have like probably 2 pages going through the TL divergence, and I think it all comes from the GAN. They have the same logic, but like underwhelmingly in the end, after 2 pages, they come up with okay, it's just the loss. So it's like they say this is untractable and this is like a bit of a parameter that okay, we're just going to use that. So it's a bit underwhelming after spending, like if you just you know read it sequentially, try to go through the math and you end up with the L2 noise. Yeah, but that's it. So they're going to do the L2 noise on the amount of L2 loss on the amount of noise. And you can do that L2 loss because it's a Gaussian data. So L2 makes sense for Gaussian distribution.
What do they do when they want to process video? Not just denoise and image and nothing.
So that's not so part of this paper, and like the stable diffusion company that are stable AI, they're still working on that. So
I see, so not proven.
So the problem with the vision is actually stability. So you can generate images, it's not that hard, but it's really hard to do it in a way that it's stable from frame to frame, because you will get like a bit of a flicker.
And they haven't combined this with like a confunet, a convolutional let's see, recurrent network. Totally free forward. Totally.
Yeah, it's totally. I mean, I'm sure people try various things, but at least on the production level, the videos, I don't think that what people do in videos, you go to fast 4 frames. and you get like a feed frame, something like that, right? Not the current.
For denoising.
Yeah, or for image, for the video generation as well. So basically, for the video generation, they would generate one image and then they were going to pass it again. And it's a bit like a retardant, but it's unrolled. It's unrolled retardant.
I would have thought that was valuable commercial application, which is blurring, stuff like that. That's very valuable. And I didn't know
Yeah, so stability AI was working on that.
Yeah.
But it's harder than probably harder than you can imagine.
Yeah, it is hard.
So it's like if you look at the results right now, they are very they are funky, but they are not stable for frame to frame.
Just to check, are you learning the future noise, or is this a type where it's xt minus xt minus 1? Are you learning the?
You learn how much between those two steps, right? You put this image and you learn how much noise you added here.
And then if you want to generate an image, you can subtract the noise there. So the input will be xt plus 1, isn't it? Or I'm misunderstanding.
Yeah. So it's xt plus 1 minus xt. The input. Oh, the input. Yeah, that's an xt. I can take a look at it. Like we better see that when we go through the code.
So this is the denoising. So you're right. You're stepping backwards in time.
Okay. In this case, the future, there's no, although there is a t, there is no time per se, right? It's just diffusion process. So yeah, but you go. It is called going forward in the diffusion process. So this is the forward direction of the diffusion. And
the neural net is trained to move you backwards.
Well, the neural net is trained to move you.
No. So you're from
yes. Yeah.
Yes. The denoising.
So
Yeah.
that's why you start.
Well, it is in the opposite direction, right? So you can see it however you want. I'm a bit right now. I confuse myself, so I'm not sure anymore. But looking at the code, it will make it. Will make it clear. Just a second. I'll probably finish the. Look at the code. Actually. Yes, let's look at it.
So the data needs to be Gaussian. Isn't it enough that the noise is Gaussian?
So
maybe that's why the formulation. First make the noise.
No, the data has to be Gaussian.
And also, I'm surprised they call it diffusion because they're not diffusing the image laterally in any way.
No,
it's adding noise.
Yeah,
That's not diffusion. You know.
Yeah.
Adding way. Noise to it.
Yeah, it is. So it's a diffusion process in terms of like adding noise, but not diffusion as in lateral. Yeah. You could probably try the blurring. I'm not sure.
I think when they add the noise, the noise is centered at that image, right? So you center a noise at that x of t and add to it, then you go to the next step, center the noise at it again, and go to it.
So
it's a random walk.
It's a random walk, so that is different. So we don't have like the same noise every.
So this is theoretically you could do that, but like in practice, because of the diffusion or the Gaussian noise, you don't need to do that.
Yeah, exactly. It's an isotropic form, so you
Yeah.
directly just get
But
one.
yeah, so you don't even do this random walk.
But pixel intensity value does that totally independently. It's not like there's no.
Yeah.
Diffusion is possibly in it.
Yeah,
Every
no,
single
yeah,
value
exactly.
is in the line walk.
Yeah. So it's a diffusion in the color space if you're talking about image. It's not diffusion in towards
At this point, hundreds if not thousands of papers have been published. I'm sure there's a whole stack of them.
Oh, yeah.
that use other noise models.
Exactly.
Yeah.
Well,
The outcome of that.
yeah, we'll try a lot of things, and it's just the basis where it starts, and so basically, and you understand that the negative, like the sampling is going pretty much backwards. It's just the different constants that you need to put there, and then actually look as well. If you look at the newer papers, they accelerate this the sampling process because, like, if you go normally, you would start with noise and you would go like 1,000 steps in order to get back to your image when you are sampling. But there's like a bunch of papers with acceleration techniques how to do basically 3 to 10 steps or something like that. And the next thing I will talk is about basically conditioning, how we condition, but we can look at the code. Meanwhile.
Could you explain what you mean by data has to be Gaussian?
Yeah. Well, the data has changed. I don't know, well, okay. So I would say it's important. Like normally, I would not talk about that. Why I started going about the data being Gaussian is, and maybe I'm wrong, but in general, I think it is important because some people want to try it with the event camera with the spike data, and it will not work because the spikes are like Poisson distributed, let's say, or close to Poisson distribution, right? And this is by adding Poisson, adding Gaussian law, it will confuse, right? You cannot add, well, you can add, but if you learn something.
Or let me rephrase my question. How is an image a Gaussian?
Well, if you take 1,000 images and you can look at the distribution of you average all you look at the distribution of the pixels in images, you will see that it is not Gaussian, but it will be closer to Gaussian rather than anything else. Imagine, like, because you're training literally for the state, if you would average 5 billion images, you will see that there is in the real world
So
there are
pixel intensities or the color intensities.
Yes.
Must be Gaussian distribution.
Yes.
Is that?
Yes.
Well, they're more like uniform, like.
Yeah. So it is a bit, I mean, I'm just kind of highlighting the fact about the Gaussian is that you would not just try to put the spike data and expect the spike result to pop out. So for the spikes, I think, and we talked today with Jason, that you probably need to bin your spikes, because if you bin a lot of data, like if you average a bunch of the Poisson, it kind of arrives, it goes towards. Sorry?
Appreciate it. Don't go all day. We've already done that.
So I shared the collab network. Sorry, collab, whatever. No, I'm
Zoom in a little bit, yeah.
even more.
Yeah.
Is it good? What?
So while we're going through this, it's important to, I mean, the purpose is to figure out how we can do stuff with vertical events and the type of data that a lot of the monitor group is playing with, EEG, that kind of thing. So it doesn't feel right to use time variant and time variant dimension in the same way that noise is projected from D equals 0 to D equals 100. It feels like it needs to go into a whole new dimension, right? So say we were going to use the DBF gesture data set and learn the normal distribution of that, then we'll probably do it iteratively. Start off by binning the entire sequence into 2 parts, and then if we get something that trains right, then split it up into 4 and keep going. And so, yeah, whatever that works on our GPU, that's going to be a pretty expensive process.
So this notebook is like a simplified version, but like a bare basics to get the diffusion model. There's some shortcuts to make it a little bit faster to train. I can train it on 800. I can train it in 10 minutes, something like that on NIST. So it's that's why it's mostly stolen code, not mine. I just cleaned it up a little. So and there is no I just use a torch vision, nothing else. So basically, the very first step we're going to do.
Sorry guys, I think we're totally overlapping the whole time. By 10 minutes already. Right. I have to go. Yeah. Go for it.
Yeah. So whoever wants to leave. There is a notebook on the line, so there is no need to follow it here. Yeah. So basically, the first we're going to generate those. Remember those alpha parameters. So basically, we're going to do the first function is generating those alpha parameters, and pretty much it's a kind of straightforward code directly from the paper. Basically, what they do is we have 1,000 steps, right? Remember 1,000 steps, and we say we have this one constant beta on one end and another constant beta on another end. Why that constant is like that, I don't know. This is something they came up in through the experiments. So it's like a one small value on one end, in close to still pretty small number of beta on the other end. So, and we're going to distribute it across 1,000 steps. And then we need to calculate those alphas as well. And then we need to calculate alpha bar parameters. And this is what this function does. And we can test it and we can see what that we get like this nicely distributed alpha and beta parameters. And then you can see next we're going to implement that basically the model itself without the autoencoder, just the model, training and sampling. The training, you can see it's pretty small. You basically generate some uniform noise, right? From the you generate a random number from 1 to t. You generate some Gaussian distribution noise, and we add this noise to our image, and we pass it through the network, and we calculate the L2 loss here. Right? And you can see that we kind of compare the expected noise here with the noise we're getting from the network. Yeah, so the code is pretty trivial. You can follow it yourself, but this is, yeah, DDPM is just name of the paper, the original diffusion paper. This class generates those that schedule so-called alpha and beta parameters that we already saw. Next is this forward function, as I described. Pretty much we randomly generate the t parameter. We generate the noise, the Gaussian here. The function generated the Gaussian, and we are adding the Gaussian noise to our image, and then we're passing through the autoencoder model here, and we are going to this criterion here is L2. We're going to check, compare the.
Sorry, guys. Those one who wants to hear about the status of hardware control through hardware neural network. We're going to talk about that right now. We have to do it because we're way over. And then, whenever you're done, maybe 10 minutes or so, you're invited to come over, as we discussed yesterday.
Oh, okay.
Remember?
Somewhat.
Do you remember? Oh, you don't remember. Okay. Then we put it off.
Okay.
But you're leaving tomorrow, right?
Sunday.
Sunday. Okay, we can do it.
Right. But we're going again look from 1,000 times steps, and we're going to start with the noise, and we're going to kind of run our autoencoder, and we're going to add it like basically this. You see, we're going to remove the noise from our image, but we're going to inject a little bit of the noise as well. So you can remove that. It should work.
Go back to your razor. But we need your razor. Nobody expects Toby.
So here you see that we are kind of subtracting the noise a little bit. We're calling them. We are asking our model, trained model, for some noise, and we are subtracting it from our image in a loop 1,000 times, and we are adding a little bit noise as well. That is just to get some randomness in. So we are not getting like it's just for fun basically. So you don't end up with the same image every time. Yeah, you can remove that. It will just arrive to the same. Yeah. And then for the autoencoder, classically you would take unit. Here it is something kind of relatively close to unit. You can see one block of it. It's a convolution followed by the batch norm and leaky relu, and we just follow it. Repeat it multiple times, and we're going fatter and fatter, and then going slimmer and slimmer again. It's not a unit because it's just a bit easier to train, faster to train. And then there's a training loop. The training loop, pretty much standard. We instantiate the DPM, we load the NIST. Now here, notice this is important. Sorry, this is important part. We're going to convert the image into the range from -1 to 1. Why? Because we pretend it's a Gaussian distributed data, centered on the 0. This is very important. Otherwise, it will not work as expected. So as a graphics programmer, I always cringe when I see something like that. It is like a very strong and naive, again, going to question, are the images Gaussian? So for some historical reasons, our 8-bit images tend to be that. So so you can do that only if it's an 8-bit per channel image. If it's if you take the data from the sensor, it will not, like a high resolution sensor, like from the camera, it will not be Gaussian because light does not do that. But yeah, if you take PNG or JPEG, it kind of works. So yeah, so if you work with EEG pointers, you will have to as well. If you need to, you have to squish it into from -1 or expand it. Okay, and then we just push it into the normal loop of the torch, training it. Nothing special here, really. And yeah.
If you want to guide the sampling, how would you do that?
Yes, it's you can. I'm asking basically if you want to do the conditional. Yeah, so that's the next step. So basically, short story. You add some embeddings. You add basically for you can. There's a multitude ways to do that. You can gate your layers. You can inject like a transformer attention in between in the unit. Inside of the unit, you would. Here you would add like this, and that's what people do. They add more attention layers here, which are controlled by like LLM, for instance. You get the embeddings from the
cross attention. No.
Yeah, but that's
in other words, the embedding is provided as input.
Yes.
Yes. Alongside.
And it will kind of gate how the data flows here. There will be injected like attention models that's going to gate the activations. And you're going to twist this. So you can imagine as well when you are going through this vector field, you can add additional force here. You can control, like with every step, you don't need to follow the vector field. You can have some additional force. Like if you have a rat or dog or cat, if you know from this position where the rat is, you can add additional force. We're going to push it from this path closer towards the rat, like conceptually speaking. But there is a bunch of ways to do this embedding. You can just, for every, just add a bunch of additional activation values.
In practice, you just like add like your text embedding with the image and
but not with your image. With every, you should do that in every layer as well. You force feed this embedding. Actually, here's the image. This is how the stable diffusion does that. Here our unit, and you can see this what I was talking about, these additional attention layers here, which are coming directly from the LLM. And the LLM kind of pushes the data here and gates the activation value. But there's you can take a look. There is probably 10 ways to do this conditioning. People obviously did that before diffusion models, just to condition GANs, VAs, whatever you want. So if we would run that code, we would see something like that. Actually, I'm not sure why my previous results. Someone probably ran not the network, but so it's going to load the NIST and it's going to train. And we're going to get this squiggles. So with the NIST, with this, because it's not a real unit, you're not going to get. I'm not getting like really nice numbers out of it, but you get like reasonable patterns from it for after 10 epochs. And if you train it for 100 epochs, something reasonable.
You compress the unit yourself.
That
okay, like that is the old standard.
Yeah. I mean, there is another notebook as well. Like if you look in this notebook, there is a bunch of links I added.
Yeah.
So there is one which has a proper unit in it. It just takes a bit slower to train. So you can try that. And off you like basically there's a bunch of pointers here that should guide you through how to do the conditioning and how to use already pre-trained models from Stable Diffusion. There's a bunch of like web UIs and whatnot that you can play with if you want. But you can see that's just the first training of the NIST. And you can see that it's Windows, but it kind of already after first epoch, you get something. So the cool thing about this model as well, about diffusion, is that what I noticed that if you train after a couple of first epochs, you can actually sense that if it's working or not. Of course, to get good results, you have to wait a long time, but from my practice, it does not take that long for you to understand if your data works or your parameters work.
If you say if I've been events to frames, this would not work because it's discrete.
No, if you don't bin, then it will not work because the events will be not Gaussian distributed. If you bin them, they will be closer to the Gaussian distribution. So I think it will work. I don't know, but eventually, yeah, you have to try.
Empirical question. Yeah, so just really, so what you're plotting now is you took some MNIST samples, put some noise in them, run your train autoencoder, got the noise and removed it.
Yeah, so now it's basically for every this image, I would sample actually just pure noise, and out of that pure noise, I would get like
okay, from pure noise
and get that, which is slowly with every epoch going to be a bit better.
Okay.
But yeah, it's pure noise.
And so run them more towards which point you're going to be affected. You don't know in advance.
Yeah, in this case, this is the simple kind of case where there's no guiding, just goes straight according to the event.
So, like in terms of EG, once you train the model, what would be like a use case?
Use case, I don't know. So it would be like we talked about that. So probably it would be like 500 milliseconds of EEG data.
I mean, now that I got the principle of it, I see why we would work on the coding and the noising. We don't have the ground truth, right? We don't have the clean EEG with all.
Yeah, of course.
This is like you have the original images, right? And you're just adding noise and denoising it. So, like let's suppose you don't have.
Exactly. So the noise EEG will be the features of the audio I'm interested in. So some language features or music features or whatever. And then the noise image will be the EEG, which contains much more activity beyond the auditory related part.
The autoencoder part is the UNet part would be the more interesting part. Once you get them out.
You are not going to use UNet for the EEG, that's for sure. You are going to have to come up with some other autoencoder. UNet is only good for the images. It's a convolutional, completely convolutional. Yeah. Take any autoencoder that you know. Yeah. Like this model here, it works without skip connections. Like shit results, but without skip connections. So it's not necessary. But yeah, take any autoencoder that works for your data. You know.
Can I concatenate the end of my network some linear model as soon as it is differentiable, right? Okay. Just to replicate like the pipeline where I just have a denoiser and then my linear model just passing the EEG and the features.
Probably, yeah, I would say yes to that.
Right? I mean, I want some non-linear denoising and then I want a linear mapping between the noise EEG.
Yeah.
Okay.
They use Apex units for fire.
Okay. Or if you can maybe throw it, if you have a link, could you put it in Slack?
This is the first example I found. The cutting face does have audio diffusion again, and basically it's a 1D unit.
Yeah.
But there's one.
I think UNet has been used for multi-channel audio, so why not EEG?
I just thought the UNet. For me, classically, UNet is very image.
Be the easiest case, I guess.
Yeah.
Is much bigger.
Yeah.
That's the EEG net as well.
Yeah.
That's the EEG net.
Okay.
I mean,
okay.
So the important thing to
Okay,
The important thing is that you have the number of samples you in and you out. It's the same. It's like if it's a time. It's not good at generating time varying.
But we can think about the data metrics, like the time and chance as an image.
Yes, so you have to think about things as an image. As long as you do that.
And if the image is Gaussian, then it's the
So the easiest way to work on this with images is just replace the images with spectrograms.
Yes, for audio.
Yeah.
But for EG, everyone.
So
there's like 1,000 steps of time migration, which you then do the denoise.
Yes.
So presumably I have my data that is not clean, and I do 500 steps because my data is already nice, and then I go 1,000 steps back. Can I expect to have cleaner data?
I don't know. I mean, so the people like no, I don't think so. But I mean, there's no reason for.
So the way we're doing it now, we're doing 1,000 steps forward and 1,000 steps back. Who's stopping me from going 10 more steps? Nobody, right? So can I go just 10?
Try, yeah. I don't know. I didn't try. I don't know what.
It's worth pointing out that like what you're getting here is just like the stock unconditional generation, right?
Yeah.
So all it's doing is making more M's. So there's like the world doesn't need more MS digits, but we'll get them no matter what.
Sorry.
Yeah. So when you start thinking about like what you want to use it for, you want to start exploring a lot of like the alternative formulations of the same process. So there's like control net where you give it an image and you give it as like you start with an image as opposed to random noise, and you give it some additional perturbation and so more like whatever. They use it for in painting, for example. So you will give it the image and you'll mask out some part of it and you fill in the part of the image according to the guidance that there's ways that you might use this for segmentation, right? So you can imagine that you start with an image and you expect that the output is the segmentation mask. And I'm sure there's like lots of clever tricks for how you get there. So like the way that these things are useful is not like this per se, but this is the way that the intuition, how do diffusion models get you to a place where you can come up with like a training process that is going to give you the types of gradients that are going to be valuable. So it's kind of cool to have like it's worth billions of dollars apparently to be able to just make pictures from sentences you type in. But as you think about how you're going to apply it on your own data, you're going to want to look beyond just like the unconditional generation into places where you're saying where we've seen it work for doing that thing that matters. And some of that might be, we've been trying to think about like the guidance. I have a hypothesis that I think is worth testing, which is that like if you start experimenting with event-based versions of this, that the guidance that we plug in is that input, auxiliary input that guides the diffusion, like that. As I understand it, there's no need for that to come from a differentiable process. So you can imagine that like you have some ability to like plug in the output of like this plugged in neural net and use that to kind of like guide the process. And so like I think there's a bunch of ways that we could get us to a slightly version of this by like swapping in stuff and then seeing that like gives us the pipeline. There you go. I see a 3, 6, and 11. Yeah, so you did 11.
That's some interesting new alphabet things.
Yeah, I think it's more Arabic than Arabic numbers, but
Also says something interesting.
so it's a 10 epochs of training. Actually, every epoch was doing not instead of 1,000 time steps, it was 100 time steps, and it's a bit of a fucked up network. So, but still, you can see it's like this is like the best thing about this. Conceptually, it is so stable that you can train. You can even if it's how baked thing, but you can train it much stable than GAN. Very simple loss. Very simple to think about it. So that's kind of the power of this model. And of course, as you're saying, like this is a DDPM. People wrote probably 1,000 papers since then. They're all improving on that. And there's like a link to this awesome diffusion models, GitHub. You can see there's like so many things.
Like stable diffusion, for example, trains up an autoencoder from image space into latent space, and then they diffuse entirely in the latent space, so it's a faster process. And then they just they decode the latent out at the end, and that's the thing that you can go on the internet and download and run on your
This point.
Yeah.
That could be, as well as we spoke with Jason today, maybe like for the spiking, you can do that. You can do some encoder that encodes spiking into something that would be good for this model, and then you decode it there. And the good thing as well is why they do that as well. They can train them separately, so they can train this on much more data. And this you might have less of like labeled data, and this you can train separately. So you can split them.
I mentioned that we did when we had Alpha to put this whole thing together. So, man, that was awesome.
No, I think it will be useful. I'm glad
it was. Definitely. Thanks for that.
Getting to the point where we started enumerating what separate projects might be exploring in parts of the space. We did a workshop a couple of years ago when a train that runs on coal and steam or a spark that ignited the landscape and then burned that much of coal out. Exciting stuff. And one of the remarkable things about this graph for me is how uniform it is. Like there are clusters, there's clusters where you'd expect them in the major forests, but these fires are the size of cities. They look like little specks, and then you look at fires like this that burn 10 million acres in a couple months. So we're at this stage now where one of these fires can pop up on a particularly bad day with high wind and dry conditions and grow to 10 million acres in the course of a month. And even if you had every firefighting asset in the world in California, you wouldn't be able to fight because this is the force of nature. This thing's letting off as much energy as a nuclear bomb every couple hours. And that's a direct result of our land management policy of the last 100 years. Essentially, there was a deal that was struck in the early 1900s that said, we will allow public ownership of lands. This is the National Park System and BLM and forestry. However, so this was at a time, this is like the robber baron era where rabid privatization of public lands or lands was very in vogue. So nobody wanted to say, okay, we're gonna have protected lands. So Teddy Roosevelt struck a deal with landowners and said, we're gonna have public lands, but the government is going to fight fires on that land. And so they, for the last 100 years, essentially had a policy of suppression, which means as soon as a fire starts, you're on the clock, you have to keep it as small as possible, you have to stop that fire. And that has effectively removed fire's natural role on the landscape for the last 100 years. So we're biologically front-loaded with a lot of younger growth that shouldn't be there. And so when we have one of these fires, there's a ton more fuel to burn and they get out of control. And then you get left with areas of land that the soil has been completely like ossified, it's not the right word, but like turn to glass, kind of. Not really turn to glass, but it becomes hydrophobic. And then when it rains, it becomes mudslide. So we have these coupled weather effects along with policy decisions taken by governments over the last years, coupled with climate change, which is a result of other policy decisions, leading us to a situation where, we have a coin flip every year of burning the size of Rhode Island or Connecticut in just one state alone. So that's bad. We don't want that to happen. So how do we do a couple things? One, we need to get better at predicting what areas are at risk for fire. We need to get better at predicting how fire spreads. We need to get better at predicting what do healthy ecologies look like. We need to get better at predicting if I have a fire which is currently managing my land for me, do I let it burn or do I suppress it? Is it going to become a 10 million acre fire or is it going to essentially peter out once it hits a particular natural barrier? So to answer some of those questions, wait, that's the copy of this. To answer some of those questions, we created a data set of 308 managed fires. So these are essentially fires that broke out somewhere, and either CAL FIRE or forestry or some municipal or local agency went out to fight it. So what you'll see here is there's a bunch of different lines. One of the lines, so this dotted line is essentially like a 6 or 12 hour estimation of where the fire edge is, where these colored lines are where fire agencies have dug a control line, either by hand or with a bulldozer. Not in the data set is where water or fire retardant was dropped, but we would like to get that in there eventually. Oh, that's in there. Okay, we have fire retardant and water drop locations, as well as drip tanks where they are.
And what are those flashing colors?
They are the VIIRS and MODIS.
These are NASA satellite.
Yeah, NASA satellite, infrared.
Okay. Where it's hot.
Basically just emittance. So it doesn't exactly tell you where the fire edge is, but it's an estimation, since these squares, VIIRS and MODIS, have like 1 kilometer resolution. So we have this all time correlated. They're kind of at different time resolutions. So you'll get VIIRS and MODIS whenever the satellite passes over. So that could be like 12 hours. Whereas these lines, the IAWF or IAFPH perimeters are entered by a person into a database. So those can either be pretty close together, or they can be not for days at a time. These control lines, I think we have a little bit better time estimation of, since we know when they were started, we know when they stopped, and we know what type of crew was put against that. So we know the production rate of a type 1 crew, which is like people with shovels, is 100 feet per hour if you have a crew of 20 people. And so we can interpolate how long it took them to do a particular line, whereas a dozer might be able to do.
But those lines are there before the fire actually starts.
No, sorry.
Oh, I see.
This doesn't
Okay.
show when they're produced, but they are timestamped for when they're produced, along with like exactly what it is. They also dig the line all across its length simultaneously, so it's not like they start in one location and go. It's like they're all across this segment as they're getting. But we have that all time coded. So we have this for 308 fires. All the fires are between 10 square miles total length or total area, and 100 square mile total area, along with all the mitigations that were taken by people. So some things we've done with this data, this is all in simulation, so this actually isn't with the data set itself. However, we took a fairly well accepted fire model for fire propagation. We put it over the operational data, which is we have like 10-meter resolution fuels data for this is all classified based on like, is it oak, is it grass, is it dead wood, or like dead spruce or something. And we also have topography. And you have to implement your own sort of weather, like wind. But then you can place your fire, have it projected, put an agent in the simulator, and say your job as the agent is to keep this fire as small as possible. That becomes a reward signal.
I see.
So we have a couple options for projects here. One, we can take a crack at training an agent. We have 2 modules that you can use. One is called SimFire. That's the thing that simulates the fire and has the game environment. And then we have SimHarness, that's where your RL agent would live, or it doesn't have to be an RL agent, but all of ours are RL agents. And this could be, you want to train a spiking control policy for a bulldozer or for a hand crew, and then or a multi-agent case where you drop them all randomly in the scenario, and their job is to keep this fire as small as possible. Or for some of our data, there's actually structures. So you can imagine that a square of dirt or a square of grass is not as valuable from a mitigation perspective as a hospital. And so your learned policy of control is going to depend on what is in your environment at the current moment. I think that's about all I have.
Thank you.
Right now.
What's that next thing? Fire line? You had this nice icon.
Oh, that's just that's the name of the project.
That's the name. Okay.
Yeah.
You guys have any question about this? It looks quite intriguing, you know, maybe a bit distant from the actual work in this group right now, but
Have you, so you mentioned you have this simulation environment basically where you can like embed these agents and see how they perform. Have you clearly have some visualization there. What's been done so far? Like what's the current state of the art?
Yeah, so we're a bit better than what I showed. What we're really looking at here is so this is stuff from like a year ago, I think. We've done better than this. We're moving towards multi-agent model-based reinforcement learning. So we want to jointly predict what the fire is going to do to inform what the agents are going to do.
But what, sorry, what's the middle panel? The left and right look the same.
It's an artifact.
Okay.
This is
the middle.
So this one is actually trained on procedurally generated terrain and procedurally generated fuels. But the topography is very discontinuous. So the thing that calculates the topography lines doesn't know what to do with it. Okay. Sorry. Yeah, so we published the data set. We're working on the scaling experiment. You know, we sort of imagine that the state action space of what we're talking about here is kind of big for any, like, imagine, you know, here, this is like 128 fuel pixels by 128 fuel pixels.
Right.
It's like a kilometer on a side, but we're really interested in areas that are like
much bigger,
100 miles on a side. And so that state action space is.
But did you use the data set to get these results, or this is just purely a simulation?
Yeah. No, these are trained on our data.
Trained on that data set.
Not on the mitigation data. So we haven't done the imitation learning thing yet.
Oh, I see.
Yeah, that's like
trained on fire spreading data.
Yeah, so we've trained these all in simulation. We have this data set which we've just published. But we have not done the work to try and learn mitigations from human examples on real fires. Our plan was sort of get the fire simulator to a point where we can replicate real fires and verify that our simulator is valid, and then use that in an imitation learning context. So right now, I mean, there's enough data to do a straight imitation learning project. We just haven't done it yet.
Thank you.
Which is one of the reasons I'm bringing it here is because it's something that nobody's done, and we have the data and we can help you, but we haven't had time for it.
Thank you for sharing that. Yeah.